Okay, now we're going to talk about enzyme catalytic strategies. This is like three-dimensional chess where everything, your board is on some sort of rotating board that's moving back and forth all the time. But yes, enzymatic strategy. Okay, so we're going to use a core set of tools you can think of them as. Or another way of thinking of them as, if you like chess, is these are your chess pieces, okay? And so a knight can do the L shape, the queen can do all these things, the rook can do only straightforward sideways, right? Okay. And so we're going to have our binding energy. That's one of our tools that we need to concentrate on. That's that core strategy. So that's the free energy released in the formation of a large number of weak interactions between the enzyme and the substrate. Again, this is the energy that's going to be released for binding and making our complex. The purpose of our binding energy is going to be establishes substrate specificity. It increases catalytic efficiency. It does two major things, right? So if we don't get binding energy back out, it will spontaneously bind. No, right? Why won't we get binding energy back out? If we have matching hydrogen bonds, would we get energy back out for binding it? Yeah, we'd get energy from that, right? What if we tried to make a bond between a hydrogen bond and a dispersion force, nonpolar interaction? That would take energy, wouldn't it? And so that does not happen spontaneously. This is what we're talking about when we're talking about this being the specificity, okay? It's literally that same matching of hydrogen bonds and such that we talked about before. The other thing is, if we're providing energy for this process, that energy is going somewhere, right? And so part of that energy is, that binding energy is actually going into things like orienting your collisions, okay? And thus it's going towards making your product, isn't it? So induced fit, this is going to be the process by which the binding energy can also promote structural changes in both the enzyme and the substrate that facilitates the catalysis. Covalent catalysis is going to be the active site contains a reactive group that will become temporarily covalently bonded, attached to the part of the substrate. Okay. I had sidestepped this up to now, okay? Because I didn't want to confuse the issue. But when you bind an enzyme with a substrate, there's two different types of interactions that can happen. There's covalent ones and non-covalent ones, okay? And so some of these interactions are not just hydrogen bonding happening. And you kind of figured that out from the previous suicide inhibitors and stuff probably, to a degree. But this would be the covalent catalysis. The example given here is the proteolytic enzyme chymotrypsin, which will bind to your substrate covalently, and through the process of the reaction will eventually unbind. Okay? They'll have that bind cut, spiced. So the general acid-base catalysis. This is going to be a molecule other than water. Is going to act as a proton donor acceptor. Some of the examples of this is histidine residues in chymotrypsin, the phosphate group of the ATP substrate from myosin, and kinesin. You have catalysis through approximation. So the enzyme is going to bring the two substrates together along a single binding surface in a manner that enhances the reaction rate. This is the one you're most used to and the one that you probably can envision the easiest. Okay? And so it's usually the example that I use the most often, right? Literally bring them together, the bang in the right orientation, right? Okay. This is carbonic anhydrase, by the way. By the way, you may recognize this a lot from organic chemistry. Remember when we were doing all those reactions where we like lose water as a leaving group? What do we always have to do? Protonate it, right? Yeah. This is what is happening there. Okay? So we're protonating or deprotonating these acceptors, okay? And that's setting your reaction up with a higher energy state. Okay, the next one's going to be metal ion catalysis. So metal ions are going to function catalytically. by several different mechanisms, but the most common ones are going to be direct coordination, stabilizing negative charges on reaction intermediates. They can also serve as bridges between the enzyme and the substrate and allow electrons to be transported back and forth. Some examples of this are myosin and kinesin. This does, you've kind of seen something close to this. This is a lot like your hemoglobin that we looked at before, right? Where we have the heme group binding to stuff and facilitating the charge change to hold it there, right? Okay. Technically speaking, if we didn't have the stuff around the hemoglobin, it would act as a catalyst making superoxide. Remember that? So we just basically do that, but we don't prevent the catalyst action. Very similar behaviors. So the proteases here are going to be enzymes that cleave proteins by hydrolysis. Proteases, cleaving proteins through hydrolysis, okay? These are going to be thermodynamically favorable. Kinetically, they'll be very slow, right? Remember that thermodynamics and kinetics are always different things, okay? Okay. So again, this is the example of this. Here we have our protein of some sort. It has an amide linkage here. What's going to then happen is we will bind our protease. It's then going to hydrolyze that bond, leaving us with our carbonate and our amine group separated. We have now cleaved those two apart. You may notice the proteases were actually mentioned before, and you've actually seen this name before. And that was in the chapter 4 when we talked about the proteases, which are the enzymatic cleaving for the proteins so we can analyze them. Okay, so the resonance structure, the peptide bonds, is going to account for its resistance to hydrolysis normally. So if we're normally in water, we can form these resonance structures, and water is going to have a very time overcoming the activation energy to do this reaction, right? Okay, because it's very stable. So the carbonyl carbon that's going to be involved in the peptide bond is less electrophilic. It's the carbonyl carbon there. And it's less susceptible to nucleophilic attack because of this resonance structure right here. This is why we normally don't get water attacking this in like an SN2 or an SN1 reaction, right? Is it has this resonance form stabilizing it. And so the then most carbonyl carbons, of course. It's more stable than most carbonyl carbons. So the chymotrypsin, this is going to be a prolytic enzyme that cleaves peptide bonds selectively on the carboxyl side of large hydrophobic residues. The hydrophobic residues are how it determines what it binds to. It's then going to make this bond right here more stable to cleave. Okay, it's going to make it easier to react with hydrolysis. What it's going to do is it's actually going to use serine. What's the time, by the way? 12:30. Okay, you take care. So chymotrypsin is going to use a serine. Again, this is a powerful nucleotide to attack a non-reactive carbonyl atom of the substrate. This is going to become covalently attached to the substrate. Remember we were talking about there's ones that attach covalently first as our enzyme substrate complex. This is an example, of course, actually the example previously used. And we're attaching to the substrate transiently. And so this is actually this process. This is the deactivation of our chymotrypsin by the DIPF, which was the diisopropyl phosphofluoridate. That's actually what the DIPF was in the previous example, by the way, that we used as covalent inactivation. Yeah. Irreversible. So what you're going to see here is this is actually serine 195 on the chymotrypsin. This is going to end up chemically modified by this reaction right here. It'll be covalently attached. This is going to irreversibly lose all activity. By irreversibly lose, we mean that you have to have some sort of enzyme come along and cleave these things off, or you have to take apart and make a whole new enzyme. One of the two. you don't necessarily have to always take apart and make a new enzyme. There are many of these processes that will happen, and you'll have an enzyme that can reverse it. Okay? It's irreversible, though, without the enzyme, if it's just sitting around solution. Okay. What does this tell you by this mechanism stopping this reaction, by the way? If we are attacking serine 195 and it being blocked means we no longer have enzyme activity, what does that tell you about that? It has to play some role, right? Yeah. And so that plays a central role to catalytic activity. If it was just a auxiliary role and it's just partially related to it, we'd have partial activity. Okay? So this is actually a phosphorus-based agent that's going to modify reactive serine residues. It actually can be a very potent toxin, in case you're interested. It's funny because a lot of the insect pesticides we use are actually just like chemical agents that would be used to kill people, but with a couple of groups added to make it so it doesn't fit in ours. So here we see the insect version of sarin. You guys know what sarin is? No? You never heard of it? Okay, so sarin is a nerve agent. It is developed as a chemical weapon. The United States actually is, if I remember correctly, the original ones that developed it. But as far as I know, we never actually deployed it in war in any way whatsoever. However, it did get deployed in the Gulf. And what it does is it actually causes all your muscles to contract. And so you die with a full body Charlie horse as you slowly suffocate to death. Yeah, it is truly horrific. If you ever see the pictures of this having been used, people die over like 10, 15 minutes in excruciating agony, which is why it's a war crime. Okay? It is truly one of the most cruel things you can do. Guess what you do to your insects if you use... Yes. So this is malathion. It's used to kill pest insects. And you notice that it looks a lot like sarin, right? Can you see that? It's very similar. It's this phosphorus group right here attached to a sulfur in this case, whereas it'd be oxygens is the one above it in the group, right? And yes, basically it's sarin for insects. You kill the insects really well, typically by suffocation. Though that's actually the primary way you kill insects overall, because their breathing ability is actually quite poor, right? Anyways, so chymotrypsin action is actually going to proceed in a two-step. This is linked by a covalently bound intermediate, of course, which we had discussed several times now, because it's just such a good example for it. The chromogenic substrate, this is going to be a substrate analog that forms a colored product measured by light absorbance. That's where the chromogenic meat comes from, by the way. Chromo as in coloring, okay? As in like chromatography. Same root word. This is going to be used to monitor enzyme kinetics because then we can see the substrate being bound, right? And we can monitor how much of our substrate binds. And so chymotrypsin is going to cleave the N-acetyl, L-phenyl, alanine, P-nitrophenyl ester to form the P-nitrophenolate, which is this stuff right here. That's the P-nitrophenolate, by the way. The P-nitrophenolate here, see that's a very conjugated color with a charge on it, or conjugated ring with a charge on it. And these charge groups are going to interact with conjugation quite well. It also has a nitro group, which is kind of interesting, because you guys will just start be covering this pretty soon. It's like the next chapters you're doing. Yeah. Anyways, this is actually quite colorful. It has a yellow color in it for it. And so every time we do the reaction here, we can see that by binding this and doing this reaction, we actually generate a yellow color. And so chromogenic substrates, again, generate colored products. They're going to facilitate our enzymatic studies because we can actually monitor them making products as they go along. Anyways, this is a chromogenic substrate. Your studies with your chromogenic substrates are going to reveal the catalysis of the chymotrypsin occurs in 2 stages. We have a rapid step, this is the pre-steady state, and a slower step, which is our steady state. And our steady state is the one that's going to get built up on and create our steady state, right? Because the rapid state is pre-steady state in this case. The steps in the catalysis are going to be explained by the rapid formation of our acyl enzyme intermediate, followed by a slower release of the acyl component to regenerate the free enzyme. Oh, this right here is the what we're acting on. Okay, we don't have the enzyme in this. Yeah, we're not actually showing the enzyme in any of these. Yeah, what we're showing is the beginning and end. So we have this. This is our chromogenic substrate. We react it using chymotrypsin, which is this part right here. And then these are what are produced. And so we're going to produce these 2 species. And those are after release. We're just showing the equilibrium for the overall reaction. We've ignored the catalysis enzyme portion of it. Because honestly, the exact binding to this is not as important. This is the acyl, by the way. That's where it would be binding, in case you're wanting to know and understand that better. Yeah. And that's the part that's getting broken in the binding site. Okay. So this is what this looks like for the 2 kinetic phase. Actually, it's pretty evident once you start monitoring your initial action of chymotrypsin. So again, this is your catalysis of the chymotrypsin. You have 2 different phases to it, and it's pretty obvious that these are not the same curve, right? Can you see that? It does not make a nice logarithmic shape. Instead of looking logarithmic, nicely curved, or sigmoidal, which would be inhibitor, right? You instead have this kind of strange looking hockey stick or something. See that? Okay, and so again, we have 2 phases. We have the rapid step, burst phase, and then we have the slow step, which is your steady state, i.e. binding. And then we have a steady state where we pretty much have bound what we're going to get bound. And all that's going to happen is it's going to go a little slower each time because we run out of substrate, right? Okay. Keep in mind this is not substrate down here. This is milliseconds after mixing because we're not measuring initial amounts of substrate we put in. We're measuring the color as it changes, right? Over time. Okay. And again, this is the absorbance. This is due to that release of this species here, right? So as this goes up, that means we're making more and more product, okay? Okay, does anybody have any questions about the material we covered so far? No? All right. You all have a wonderful 19 minutes. I basically have everybody in biochemistry